So, okay, so today I want to talk about one part of my group topic, which is about the phenomenon of heating in materials and basically how things get hot when exposed to light and how they evolve. So it's a fairly simple question, and I mean, maybe the schematic is a little bit rough, but the idea is you have a material and you shine light on it, and you expect that the material will absorb energy, and what you want to know is what happened. Where does this energy go? I mean, eventually you know that it will go in the form of heat, but how does it happen? When does it happen? How long does it take? And what can we do with it? Is basically the topic of today. So as Professor Stell mentioned, I'm a scientist at Argonne National Lab, which is located near Naperville. Actually, I heard the noise, but the name earlier. But it's actually somewhere we should have gone, I think, as part of the REU. I think every year we have a visit of Argonne, and it's actually a very nice place. There is a synchrotron, there is some leading computational facility. So I realized this year nothing worked fine, but I hope let me know. You can drop me an email in the coming months whenever we are able to return on site, and I would be glad to host you there for a visit. So I'm also appointed at Northwestern through this Northwestern Argonne Institute of Science and Engineering, and this is what brings me. I'm really glad to have this opportunity, and because that gives me the opportunity to work with REU students every summer now, and so I'm very much looking forward to continuing this in the future. So the Center for Nanoscale Materials is something I would like to brag a little bit about. You may not know about it, but this is a center which is now 12-year-old. It's one of 5 nanoscale science research centers in the country. There is one in Berkeley, one at Brookhaven, one at Argonne, one in New Mexico, delocalized over 2 sites, and one at Oak Ridge. Those centers were created at the beginning of the 2000s. And the idea was to have staff scientists such as myself work half of their time on their own project with whatever they please, and half of their time helping users, interested in nanoscience. And because nanoscience is such a field where you have people, coming at it with physicists. I'm a theoretical physicist by background, but also chemistry, material science, biology. Because of all those fields being represented in the same place, it's sometimes really hard to find the right expertise. I mean, it could be that for you, accessing an electron microscope is very easy, but it could be that in the nearby department, nobody has access to that. And so those centers were created to kind of give access to tools and methods, and for example, for me, theoretical tools to make that available for users. And so just to mention, so that comes at no cost, and we have actually of undergrad students using those tools because we have staff scientists to help you using them, and so it's a relatively safe environment. Not to criticize the university, but we have actually a lot of safety measures. We have a lot of training encompassed in those tools, and so please contact me if you have any question on that. You can access at no cost nanofabrication devices, FIBs, electron microscope, ultrafast spectroscopy. You will see some of those data actually in this talk. And of course, you can use our computer cluster and the codes that we write, for example, in my group. So just, there was some shameless advertisement, but please contact me if you have any question on the centers, because I do think, this is a place where we have a few students and they are all very happy. Okay, so this is actually my group. As part of this center, we have on the order of 30 staff scientists, and I'm one of them. And right now we are 7 in my groups. So Sridhar Sadasivam, I will show his work. He's not in my group anymore. He's now a staff scientist at Intel. And I have 2 postdocs working with me. One of them based at Northwestern, Shunfei Zhou. She's actually supervising Bukuru. So she's around. So normally we are delocalized over 2 places, Argonne and Northwestern. Right now we are all delocalized in our basements. But it's basically I have a presence in both sides. So I have two postdocs, Shunfei and Srilok, working in basically property of nanoscale systems, and particularly with application for quantum information science and sensing. I have 2 visiting graduate students, Anubhav Andar, who works on plasmonics, and Kevin Risco, who works on inverse design and AI. And I have 2 undergrad students, Bukuru, that I presume all of you know, working also on mixed dimensional heterojunction, and Dan Palmer with a SULI program working on data infrastructure for nanoscience. So basically what we are trying to do in my group are things related to information and energy transport, that's my background, but in the more general context of current trends in material science, such as mixed dimensional heterojunctions. That's part of the Mercer Material Research Center that hosts all of you, if I believe I'm correct. And there is also the larger context of AI for science. You probably have heard a lot about AI, and we are kind of having a lot of fun trying to apply some of those artificial intelligence methods to the context of material science, for example. All right, and so today, as I mentioned, I will talk about what Sridhar has done when he was before moving to Intel a few years ago. And that was in collaboration with some people at Northwestern, Professor Richard Challer, particularly. He's in chemistry department. Maybe some of you are working with him this summer. And also people at the doing X-ray spectroscopy at the Argonne Synchrotron. All right. So, as I mentioned earlier, the problem we have is relatively simple conceptually. We have very big lasers, which have a lot of power, and we can basically shine very briefly the equivalent of 100,000 sun on a material. And heats up, that there is no mystery in that, right? We basically shine light and material heats up. And the only thing we care about really is what's the profile of temperature as a function of time, okay? So, I mean, all of you are as familiar as I am with the concept of temperature. I mean, we experience it every day, right? And with the concept of atoms. At least for myself, I had a lot of difficulties bridging the two, right? Because I mean, those are two different concepts, and we don't frequently put them together. So here is a video I stole from YouTube, so hopefully it works. One thing I would like you to think about when you're thinking about like, how do I think about the temperature of an atom, is really the concept of large number, okay? It's really the question of regression by the mean. So let me lower my volume. Hopefully it doesn't blast into your headphones. So I don't know if you can see it, tell me if not. So that's actually a toy, okay? That illustrates the question, what we gain, what is the concept of temperature for atoms? So you see, imagine those small, pieces of metals are actually atoms, and they can go through all type of trajectory. And what you see at the bottom of the screen right now, if I stop 1 second, what you see here are just scatterer, okay? So randomly, every single of those balls is going to bounce back, left and right, left and right, left and right, left and right, okay? And of course, at each step, it can either bounce left or bounce right, right? So in a mechanistic approach, what you're trying to compute is, the trajectory. So you're trying to follow every single of those individual balls, okay? Figure out where they bounce and where they end up at the end, okay? So that's very powerful in quantum mechanics, that's what you do, for example, right? Or in classical dynamics, that's what you do. Or in molecular dynamics, if some of you are doing that this summer. Basically, so that's the concept of atoms. Now what I want you to think about is what happens if, I mean, you just can't follow all this trajectory. On top of that, in that case, they're pretty random. And so you're saying, you know what, let's forget about individual trajectory. I don't care if this particular ball makes it to this particular basket at the bottom. What, in fact, I just assume that instead of having one ball, I have a lot. And the concept a lot will come a lot in this work. So I mean a large number of those. And you know that just by virtue of probability and deviation from the mean, if you scatter a lot of them, you will always end up with this type of distribution, okay? You can rotate this thing 1,000 times, and if you have even more atoms, because in a real world, even a gram of materials have infinitely more atoms than this, you will always end up, regardless of what happened to individual trajectories, okay? You will always end up with something that looks incredibly boring, just a distribution, just a line, right? And so that's something which is very important for all of you to understand. We are just by abandoning the idea of trajectory and just saying we have a lot of atoms in the system, we are able to describe the system in an incredibly powerful way, which is just this simple distribution. So forget about what happened to every single atoms. Just look at them as a whole. And at the end of the day, you will have something that is a thermodynamic quantity that look a lot like what this curve is. This is a thermodynamic average of the position of the atoms at the end, okay? And this is just described by the fact you have a large number of those atoms in the system, okay? So that's an important analogy to do, okay? Because as you will see in the next slide, we can actually compute the trajectories. And if you look at the system as a whole, you will extract temperature, okay? So this is, the macroscopic view. There is nothing quantum into that. There is nothing about, statistics into that besides a simple law of probability. And that's a binomial distribution you will end up every single time. And the larger the number of atoms, the more certain you are so that your final line will look exactly like that. Okay. And that, I stole that from YouTube on this website. I can send you the link if you want. So the good thing with that is because we can describe this infinite number, practically infinite number of atoms with a single variable or a distribution, we can extract very powerful concepts. So this is, an example of what I was looking at in the previous slide, right? I'd say we are shining light and a lot of light in a very short time. And we are looking at basically how the materials react to this light. So this is, an example that you can extract from statistical mechanics as well. So what you're seeing on the left side, I don't know if I don't have a pointer, but on the left side of the screen, what you see is a stone that we took from Door County because we must add, I don't know, they have to steal stone from everywhere we go, but that's a small rock, and basically which was heated by the sun recently on my deck, and the experiment we are doing was to throw this hot rock into cold water. Okay, so basically, and you will see that there is a lot of analogy to be drawn just based on this example, thanks to this power of statistical physics. So at t equals 0, we have a hot rock, and at t larger than 0, we have dropped the rock, and we are looking at the temperature of the water. And the question we're asking are, is the temperature of the water everywhere the same? If not, how does it look like? Does it look like a distribution, a smooth distribution or not? And also, the final question we are interested in is how long does it take for the temperature of the water to be the same as the temperature of the rock? Okay, except we do that with atoms, but this is exactly the same case. So again, I say the magic of thermodynamics and statistical physics is that because you have those average and this deviation from the mean, I cannot be too wrong in what I'm going to say today. The rest, I could be somehow wrong, but I cannot be wrong for a long time because we know exactly what happened at the end. All of you know that at the end of the day, regardless what I do, the temperature of the rock will be the same as the temperature of the water. So we know that if we wait enough, meaning if time goes to infinity, we'll be in equilibrium and everything will have the same temperature. Okay? There are even more things we can actually know. We know that if we use a big rock or a small rock at the same temperature, let's say you have a big rock and small rocks that you introduce, let's say 350 Kelvin inside the back of water, inside the bucket of water, you know that the final temperature will not be the same, right? And that's because those have different heat capacity. So heat capacity is in joule per Kelvin, and that tells you so that CEL, in that case, that's the heat capacity of your electrons, which absorbs the light. And that tells you how much energy is needed for to increase the temperature of an electron by 1 degree, okay? And similarly, if I put a large bucket of water or a small bucket of water, you can imagine that the final temperature will change. And that's because there is a heat capacity, the C lat, the heat capacity of the lattice, so basically the atoms, okay? And again, we know that by virtue of thermodynamics, at the end of the day, the equilibrium temperature will be the same for the two. So we know that the energy that will remain with the electrons, that will remain with with the things that absorb the light, will be proportional to this final temperature and times the heat capacity of the electron. And for the energy that will be in the water bucket will be proportional to the heat capacity of the lattice. Okay, so that tells you that. Basically, if you have same temperature everywhere, the partition of energy is different. Okay, one part will have, if there's a larger heat capacity and the temperature is everywhere the same, the energy is larger. Okay, that's a simple concept, just joule per Kelvin. It turns out that I'm not going to do the derivation, but I think maybe some of you have done that in class. If you take the heat capacity of electrons, it's proportional to the temperature, while the heat capacity of atoms is proportional to the cube of the temperature. Okay, so what it tells you is that room temperature for most atoms, for most materials, almost all the energy you give to electrons with light will end up in the atoms. Okay, so at the end of the day, you will have everything at the same temperature, but the amount of energy that will go from atoms to the atoms is much larger than what will remain in the electrons. Okay, so you're really looking at the energy transfer where at t equals 0, all the energy are with electron, and at t equal infinity, most of the energy is a lattice. Okay, so that's things that cannot be wrong. Okay, everything else, I'm one referee report away from being wrong. This is actually, thermodynamics, and we cannot go beyond that. So at t tends to infinity, we know what is happening. Okay. All right. So I mentioned earlier that the analogy about this analogy about what thermal physics is for atoms, we can actually do those calculations. We can simulate the trajectory, and this is how it looks like. So this is a molecular dynamic simulation at a finite temperature. And the material you're looking at is tungsten disulfide, which is a fairly popular material those days for it's a two-dimensional materials. You see that there is a layer structure, it's like a sandwich out of plane in the z direction. And you can actually propagate that as a function of time. You can use powerful solvers to actually compute that. And that gives you, and that is basically what tungsten disulfide look like at room temperature. Okay, this is what the atoms look like. This is how they move. Okay, so there is a lot going on, and as I mentioned, it's very similar to like those balls falling down at the same time. We don't really understand that, but what I can tell you is that if the system is large enough and if the time is long enough, if some of you are from a chemistry background, they know that every atom will have received the same kinetic energy to move in every single direction. Okay, so that tells you sulfur is much larger than tungsten, for example. So sulfur will have moved a lot because the kinetic energy of sulfur is proportional to the mass. So the amount of motion per kinetic energy is going to be larger. Basically what it tells you is over time, when you look at this trajectory, every single atom receives enough energy to move out of plane, in plane, or with respect to the other. Okay, that's what is called equipartition of energy in classical physics. So that if some of you are from a statistical mechanics background, that when you think about temperature for atoms, that's what I would like you to think about. If some of you like me are physicists or material scientists, that's not exactly how we think about. We don't think about kinetic energy so much, like what we did just now. We think about vibration in solid. We think about phonons. Okay, so phonons is, for example, when you have the speed of sound in a material, you're looking at waves like that. So you're looking at oscillations of atoms at a given frequency, where atoms can move in phase. That's called acoustic phonons, or out of phase is called optical phonons. Okay, so you can also think about those atomic vibrations, which are just property of a solid or materials, where you consider how do atoms vibrate in phase or out of phase with respect to their periodic images, and from there you can get an energy, and you get generally what is called phonon dispersion, which is an extremely important concept in physics. And I don't know, some of you may have seen that if you have taken quantum mechanics as one of our first examples. What you are seeing here, for example, if you have two atoms per unit cell, so if you have, let's say, a material like hexagonal boron nitride, you will have two branches. And one is acoustic. Acoustic just means that all the atoms are moving out in phase. And you will have optical, which is when two atoms move so they move towards each other as opposed to moving together in the same direction. Please, again, don't hesitate to interrupt me if you have any questions about those concepts. So those are the things I will build upon in the second part of my talk. So please interrupt me if you want. So when you think about temperature, so this is an energy. If you think about temperature, the only thing you're saying is that all those vibrations are there, and they're happening in the trajectory I showed you earlier. They're happening at the same time, and they're happening with different, likelihood. And the likelihood is given by what is called a Boltzmann distribution. So it's just, the likelihood of this happening is inversely proportional to the energy. Okay. So again, if you come at it with a statistical mechanic background, you will think about heat as every atom receives the same kinetic energy to go in all directions after a long time. If you think about it as a physicist, you're thinking about phonons being occupied in a statistical way by a given, energy distribution, which is plotted on the right side here of the screen. All right. So that's at T equal infinity. So that's when things are thermalized. So that's what we know for sure. Here's what we don't know. We don't know when is that. So we are trying to know when things get hot. And so we know when, time equal infinity is not very useful for that, right? So we are trying to see when can we actually approximate this to be the case after shining light. And also we are trying to say how, because I showed you the toy earlier, but it's kind of a boring toy if you think about it, right? You turn it 20 times, you have 20 times the same answer. It's always a binomial distribution. And that's just because you are bound by, mechanics, by statistical mechanics and by thermodynamics. It never fails. But at short time, it can actually fail. So on the way back to this equilibrium, in principle, you could have crazy distribution of energy where one atom would receive way more energy to go in one direction than the other. Okay. And so that's where kind of the fun physics happen. As a physicist, that's where prior to this time equal infinity, wherever that is, you can have all sorts of distribution of energies and see what happened at this point. So there is a real question of what is happening when materials heat up. So effectively what I define is two timescales. There are timescale, which is an electron lattice equilibration timescale, which is just like, when are we at equilibrium? And there is another timescale, which is when do things look weird, you know, at which, when are things looking like a nice distribution like that, and when are they not? And that's called the intralattice equilibration. So again, that's what we are after in my group. You know, when does electron lattice thermalization occur? When do those non-thermal effects, in the sense that, you know, you cannot model that with a standard distribution, happen? And of course, what we want is to control those timescales. So, you know, the idea on that is, where if we are able to control how the energy is distributed in the material, can we make use of that? And the answer is yes, actually, for many applications. The idea is to get the materials that get, you know, hotter, slower for thermal transport, for example, or materials that cool down faster. That has a lot of application. You may know that in microelectronics, thermal relaxation is actually an essential problem right now. It's probably the thing that prevents your computer from being the most powerful right now. It's that one of the bottlenecks is the fact that things are heating up enormously, and we don't know how to get this heat out. And so that's what we are basically trying to do here. Okay. All right. And, you know, the real question, of course, is why does it matter? You know, why am I even talking about that? So just to give you a sense, if you have a device you know, typically I'm a center for nanoscale materials, right? So nanoscale is, you know, is typically the type of, a nanometer is typically the scale I'm interested in. So if you have a device which has a characteristic length scale of a nanometer, and you're considering that, you know, atoms move with a sound speed, let's say, speed of sound, so that's a kilometer per second, right? What it tells you is that if everything I show you in the next, if anything happened below a picosecond, it doesn't really matter to us. I mean, it means that, you know, by the time heat gets out of the device, it's basically the heat that thermodynamics thermodynamics predict. If it is more than that, then it means that we have to do some correction to our current computers, for example, or to our current understanding of our computer, at least, to know what is happening. And it's a problem, it's a long-lasting problem in microelectronics that some of you may be familiar with, which is called the phonon bottleneck problem. It's actually exactly what I'm showing right now. It has a lot of impact in the stability of nanomaterials and interfaces. So we know some of you may be right now working on lead-halide perovskites. That's a very popular material for new generation solar cells. They are extremely unstable under light, which is unfortunate for a solar cell. You will have to admit. So we don't exactly know why they are unstable, but we know that when we put them under light, those materials like basically dissolved. So we need to understand what's happening thermally for that. It's also important for people, you know, maybe some of you are doing those type of measurements of thermal conductivity. So a lot of those two-dimensional materials that I will show in the next, they are fantastic for thermal conductivity, actually. The problem of transistors that I was mentioning, those phonon bottlenecks, they don't really exist in those materials. But we need to measure, we need to know how thermally conductive are they. And the question is, the only way to do that right now is to shine a laser. And so it's a real question. If you shine a laser to measure thermal conductivity, for example, are you really measuring the thermal conductivity? And that depends on those effects. That depends if a laser hits a material normally or not. So that's one. So it's more like a validation of materials problem. And also, I would like to say that, I mean, there is an insanely exciting moment in science right now, which is the coming of age of what is called free electron lasers. So I don't know if some of you are familiar with this, but it's basically new sources of X-ray that are basically an X-ray laser. And so we have one in the country. It's at Slack right now. It's a fairly pricey installation, so I don't expect that to have so many, but it's basically a few $billion just to install the thing or to renovate it. But basically what it tells you is a laser of X-ray, and that allows you to basically have snapshot of atomic positions at an extremely short time. So femtosecond, you know, movies of atoms moving. And that's something that when I started my PhD in 2005 was not existing. Okay, so that's really a revolution that has been coming in the past years thanks to the new probe. And so there is a real need on the theory side, which is my side, to kind of bring some understanding of, you know, what we expect to see when we shine a laser on something and we have a snapshot of those positions. So that's a big motivator on that. So we can actually probe whatever the I'm saying in the next, we can actually have experimental validation or invalidation coming, which is something really recent in the past 10 years. All right, oh, sorry. So I'm going to pass through you don't need to look at anything on the slide besides the fact that my group has done quite a bit on, lead-halide perovskites, silicon junctions for low-key dielectrics, two-dimensional material, cubic semiconductors. That's something we have gone through for a range of materials. Right now, I'm just going to talk about, mostly cubic semiconductors because they are the simplest and they contain the same physics as the other. But please ask me about the other ones. I will talk briefly about two-dimensional materials, which are of relevance to the Northwestern Material Science Department. But if you have any other question on lead-halide perovskites, some of you are doing some summer projects on that, let me know, and I will be happy to comment. All right, so I will briefly show you what I'm doing, how we are thinking about those problems, and then I will move into our conclusions for the materials or how heating happens. So basically, so that's going to be the only page with significant formulas. As I mentioned, temperature is every atom receiving the same amount of energy to go in every single direction. Okay, so going beyond that is actually fairly simple conceptually. Is to say that each atom can receive a different amount of energy to go in each direction. Okay, so basically we go from one descriptor of every atom receives the same energy to atom specific or vibration, actually direction specific, and that's what you are seeing on the left side on the right side of the screen, which is the mode dependent temperature, which is just how much energy did this mode receive to go in that direction, or this atom receiving to go in that direction. And so that's a function of time, of course, because we are looking at what happened when time is not infinite. And similarly, there is the same concept. Some of you may be familiar with that if you have taken solid state physics, which is a level-dependent occupation function for electrons, which is called a Fermi-Dirac function most of the time. And so both of them are a function of what is the nature of the mode. So is that acoustic or optical for phonons? That's a factor nu and n. And both of them are a question of quantum numbers that maybe you're familiar or maybe you're not familiar. Let me know if you're absolutely not familiar with that, which has to do with the translational symmetry of a crystal. So basically are two atoms next to each other in phase or out of phase. Okay, so that's basically what K means. It's a wave vector. I will show you a concrete example of how that plays a role later. And so we have to have those fundamental variables, which is just basically atom and direction resolve temperature, and same for electrons. And now we need to know how they interact, right? So it's a fairly simple problem to ask. And the interactions are, is basically, you can imagine you have an electron going at a given energy, and you can bump into a phonon, and you will change its energy, okay? Similarly, you can have two phonons coming, or two vibrations coming, two atoms bumping into each other, and creating transferring their energy to a third one, okay? So that's the type of interaction. So I use the word phonon, but it's interchangeably with vibration for the next. So just don't let that influence you. It's just atomic vibration, bump into an electron, what happens to the electron, what happens to the atomic vibration. Similarly, two atomic vibrations bump into each other, what happens to the third one. Okay, so that's all we are considering. So we have our fundamental variables and we know how they interact. We just have to compute it now. And that's actually a bit tricky. And so I mentioned, this idea of conservation of this quantum number named K, and which is a descriptor for things being in phase or out of phase. And so simply, if you think about an atomic vibration and how it impacts electrons, it's simply a gradient. So all of you have actually solved harder problem at school as part of your mechanic classes or Newtonian mechanics. And the idea is you basically have to compute how much does the electron energy change as you move the atom. So it's a gradient of energy with respect to displacement. And just to mention, to give you a taste of why is that hard to compute, or why is that, where is the technology there? Just imagine a mode. Let's take the previous materials that we liked, so tungsten disulfide, sorry. And let's imagine a vibration mode where all atoms move in phase, all the tungsten atoms, sorry, move towards the top, and all the sulfur atoms move towards the bottom. So I know there are some chemists among you. So you know that tungsten and sulfur, if you put them together, sulfur is going to take charges away from tungsten, and so the material is ionic. And so you know that if you move all the atoms of the tungsten atom up, you're going to move all the charges in the materials up. Okay, And similarly, if you move all the sulfur down, you're going to move all the minus charges down. Okay, so if all those atoms are in phase, which is what is at the top of the screen, basically you will create a net dipole. Okay, so you will, for electrons don't really care about atoms; they just care about electrostatic potential, right? So they are moving, and if you have a plus, that's good. If they have a minus, they are not really happy, right? So basically, as the atom moves, you're going to create plus and minuses in your positive and negative charge in your material, and they will see that. And so what you see is the difference between top and bottom is just a phase factor, how those two consecutive pieces of materials are moving in phase or out of phase, the same mode, okay? And what you see is that for an electron, in one case you will see a dipole, and in the other, I don't know if you're familiar with electrostatic, but you will see a quadrupole. And so what it tells you is that the electron is going to be happy in one case, but not the other. Okay, so you really have to represent that, these interactions, those fundamental interactions that kind of account for how electrons see atoms in your method. So I'm gonna skip this part, but basically we are starting with hot electrons, and they move and they are heating up. And what we are gonna look at is how they heat up the atoms based on those computed quantity of those interactions that I just proved. So let me actually. So what we need for that are standard theory. So some of you may recognize those terms. I'm not going to explain that in this talk, but please ask me about it. One of them is called density functional theory, and that's kind of the standard tool for everything which has to do with material science. For 99% of the periodic table, you're able to have some good representation of what the energy of electrons in a given in a given atomic landscape. So we use that. That's a standard tool that was not developed by us. We can just reuse that. Similarly, we have the same thing for those vibrations. We can compute them from the same code. We move the atoms and we compute the energies. That's all. We have those interactions that I just explained, and we compute. We display things in all sorts of ways, and we have the interaction between molecular, atomic vibration. So I can answer on that. It's not that important for my talk, but we have found a way to compute to take everything together and compute them, and that's what my job looks like basically. So basically, we compute occupation functions as a function of time. So that's how it looks like. All right. So what I'm showing you now is the result. Okay. So what you're about to see is how does the material heat up. I put two materials which look a lot the same. They both have a diamond structure if you're familiar with it. One is called cubic boron nitride on the left, and the other is called cubic boron arsenide on the right. Cubic boron arsenide is actually a cool kid on the block right now of materials because it has a thermal conductivity which is predicted to be larger than the diamond. So there is a very active field of science on studying this material. I'm happy to, anytime that arsenic is mentioned, I'm happy to be a theorist. I don't know, I wouldn't, I'm not sure how safe it is to study that experimentally, but there is actually a lot of synthesis going on to actually synthesize good sample of these materials right now. So what you're seeing are vibrations. Those are, as I mentioned, those are atomic vibration. What you're seeing at the bottom left, I don't know if you can see my pointer, but at the bottom left are those acoustic vibrations where all the atoms in the material move in phase. Of course, based on how you move, it can be transverse or longitudinal interactions. So there are all sorts of fun wave physics to do. And there are optical excitation, which are higher energy, where boron and nitrogen bump into each other. Okay. And you see that those two materials, they look a lot the same. They have the same crystal structure, but their vibrations are quite different. Okay? And one thing you can think about immediately is that boron nitride, they are very next to each other on the periodic table. They always have the same mass. So the idea is that one move one way, the other, basically both atoms look a lot the same. So if you move one versus the other, it doesn't change much in energy. Boron arsenide, on the other hand, arsenide is much more heavy than boron, and you can imagine that atoms of arsenide cannot move as fast, for example, as light atom of boron. And so that's what you're seeing in the phonon energies. Okay, anyway, I put some hot electron into my system at T = 0, and I'm gonna watch this thing heat up. So that's what you're seeing, okay? So as time passes, what you see is that the first vibrations that became hot were the high energy vibration, okay? And so basically the way you heat up is first the energy of the electrons is absorbed by those high energy vibration, and you see as time passes, and those are picoseconds, so they are relatively short times. As time passes, you see that it becomes hotter and hotter everywhere, okay? You can ask the same question for boron arsenide, for example. And this time, you have a lot of the same physics going on at slow time. you see that those high energy vibrations, they accept energy, they receive energy from the electrons, but you see that the rest actually of the device, the rest of the vibrations, sorry, do not. Okay, they stay cold. So I don't know if that's clear from the, if you don't understand this video, please let me know. You can actually continue to propagate that in time. We have, we have built a solver to just do those, to compute those temperature as a function of time. And that's what you get. So after 20 picoseconds, so if you remember my warning at the first, it was like, after 1 picosecond, it gets interesting. So you see that after 20 picoseconds, which is larger than that, on the left side, you actually have something that looks uniformly heated, or kind of uniform at least. So you can say, well, most atoms are at, 450, let's say, most vibrations are 450K. On the right side, on the other hand, only a fraction of the materials are heated up. So only some of those vibrations, only some of those directions have been heated up, not everything, okay? And so, so basically, what it tells you is that after 20 picoseconds, we are still not in the regime where things have heated up and we can consider thermodynamics to be reliable. So that's actually good news for me. It's bad news for common sense, but it's good news for me because it means there is something to look at and try to understand. And so the way we understand that normally is actually what is called the two-temperature model. Okay, so remember so the idea is to say where I had heat in my electron, I had a cold lattice, I put them together. So in principle, maybe together they come into a midpoint. So what the size of the circle here is just proportional to the heat capacity, and so at the end of the day, you will expect that everything is orange, right? Everything is thermalized. So that's how we have been, for close to 30 years now. We have been considering how those systems heat up each other in this form with two temperature. And if you remember the previous slides, it's kind of a problem, right? Because I mean, what I'm saying is some of the atoms are very hot and some of the atoms are very cold. So how do you extract one temperature? So actually, that's a real question for us. It looks like this phenomenology of seeing atoms are cold, but they're getting hotter, and electrons are hot, but they're getting colder, is not exactly what happened, because, or at least it doesn't happen uniformly for the atoms. It's actually, we can actually test that. We can see that this model of considering things at one temperature and coming together fails miserably to basically detect that. And so that's a real problem for us, because we need to be able to do better. We need to be able to tell an experimentalist how it should be on the sample to observe, to have, for example, better transport or better heat transport. So we need a better model than that. So people have proposed, to do a three-temperature model. So what happens if, we consider that, well, you remember there was those high energy vibrations that heat up really quickly, and those low energy vibrations that heat up very slowly. So what about we just partition them? And we say that, that atoms are like two temperatures. There is a temperature for optical, temperature for acoustic. But we can test that again. So this time we have a temperature as a function of time that is plotted on the right. So you have the electronic temperature, we have the optical range temperature, acoustic range temperature, and we can compare what our model is saying versus our simulation. And you see that, the good thing is we kind of capture the fact that there are several temperatures, so it's good. But the bad thing is that we are not quantitative. Particularly, we are saying that electrons cool down super quickly, when effectively what they do is that cool down very slowly. Okay, so there is a real trade-off coming up. So as I mentioned, we are dealing with thermodynamics, so we know that we can just add the number of atoms and we'll get the right solution. So we could imagine, we could say, well, maybe we should partition in more groups. So we could have one group of vibration, another group of vibration, another group of phonons, and so on and so forth. So the problem with that is then if I go to my experimental colleagues and I say, yes, I have a perfect partition of my system, and this thing, and you have to fit those equations based on experiments, they will not be happy, okay? Because each time you add one of those subparts, you basically complicate the system. So you're making a system which is extremely complicated for that. Also, I would mention that in our simulation, we have 50,000 different temperatures. So we know basically the right answer is anywhere between 3 temperature and 50,000 temperatures. So it's not clear when exactly we stop. So instead, what we have developed is a way I understand how things heat up under light is what I call successive summarization. So if you look at electronic temperature as a function of time, and the temperature of those hot vibrations that basically suck energy immediately, you'll see they are very close. So for example, after 20 femtoseconds, if you look at, ask your code, what's the temperature of your electrons? And it tells you 2000 Kelvin or so. And if you look at the temperature of hot phonon, which are on the left side, they will be at 2000 K as well. Okay. If you continue to propagate as a function of time, and you stop, for example, at 500 femtosecond or 0.5 picosecond, what you see is that if you ask the electrons, what are your temperature? You will see that is 800 K. And similarly, if you look at what the temperature of vibration, this time you have way more vibrations which are involved, right? Which are hot, but they are all at the same temperature. They are almost all at the same temperature as the electrons. Okay, so what it tells you is that really what happened is that some vibrations suck out some energy from electrons, immediately we have the same energy. After a while, more vibration became involved and suck out some energy from electrons. Everybody has the same energy, and the rest is cold. Okay, and we can keep going, and we can actually prove mathematically that this is what is happening. So again, the picture is more and more of those vibrations are in contact with electrons as a function of time. It's a fairly simple picture. So that basically, that's it. That's what we understood. We have those. Sorry, it doesn't look super fancy, but it really is not. At time equals 0, we have hot electrons and hot phonon and cold phonon. At time larger than 0, we have hot phonons, hot electrons, and some part of the lattice just did not care yet about electrons. Okay. Wait, sorry, I was supposed to. So that's basically our model. Okay. So if I come back to my image of a rock in water. So I start with a hot rock, I have cold water, and I want to know what the, what the water temperature is as a function of time. I tell you that, the first two temperature picture is like all the water in the bucket is at the same temperature, even as you put the rock inside, okay? So in that case, you have a limiting rate, which is just, when does the temperature is the same? When is the temperature the same everywhere? That doesn't work. What people have proposed are, what some people understand on that is that, well, in fact, you should have, because you have this gradient of temperature, it's kind of obvious from this picture, right? You have, of course, the water close to the rock is going to be hotter than the water far from the rock, right? So as a function of time, you basically have a limiting rate, which is both, the difference of temperature between the water and the rock, but you also have a limiting rate, which is like how quickly the water can propagate the heat, right? And instead, what we propose in this case is a model where, the way we understand it is, in fact, you are not really dropping the rock inside the water, you're pouring water onto a rock, okay? And you see that besides making a mess on my deck, this actually corresponds to, this is similar to, the limiting rate in that case is how quickly she's able to power the water on the rock. It's not the rock conductivity, it's not the rock-water interface, is just how quickly does the water come into contact. Okay, so that's kind of a model we have pushed forward in the past years, and that's how we understand heating in material with light. Okay, I just want to mention those are actually equations I can solve, and I'm sure you can solve them too, because you're probably much sharper into your algebra than I am at this point of my career, but it's just basically taking the same rate equations that we had before and making them time dependent, okay? And so those are accumulation functions. I'm not going to go into the details, but they are extremely simple functions to solve. And that's a model that appears to be quantitative for a range of materials. I will skip that, but sorry. Yeah, so I will move. So that's basically what I want you to remember from the first part, and you will see it applied also to the second part of the talk, which is about two-dimensional materials. Sorry, I'm realizing I'm running a little bit out of time, so I apologize for all the skip slides. So basically, we have understood how it works for cubic materials. And for two-dimensional materials, what I'm going to show you is that it works a lot the same, except that there is one more degree of freedom, which is actually result in some fairly fun vision of what heat means, as you can see. So we have done it in graphene. I think graphene is very little at this point. That's, that's two-dimensional carbon. It's a popular materials. The people who have, exfoliated it first from graphite won the Nobel Prize a few years back in physics. And, as you would assume, it has a vibration dispersion that involves both atoms moving out of plane or in plane, okay, as you would expect. So a lot of the reasoning that we have done before works, and we can actually, launch this movie again, where we put hot electrons in graphene, let them relax their energy, and let the graphene, vibration equilibrate. So I'm going to show you a video now of how it goes. Once you do that, you have a lot of the same picture I was discussing before, right? You have this vibration at high energy that absorb a lot of electronic energy that heats up very quickly. and you have the rest of low energy vibrations that heats up slowly. So nothing new under the sun at this point. One thing that you may not have seen in those 20 picoseconds going into like 5 seconds right now is something else happened. So of course, the phenomenology of high energy, sucking energy, high energy vibration moving first, low energy vibration moving second, that's still hard, but something else happened. The vibrations that suck out energy turn out to be entirely in plane, okay? And you can actually plot that. Let me plot that differently. But the idea is all the branches that involve vibration in plane heats up very quickly. And all the branches that involve vibration out of planes heat up very slowly. So that's something which is weird, right? Basically, what I'm saying is you are heating up first in plane and out of plane. So you have heat, but you have heat in plane and you don't have heat out of plane. So that's kind of it's kind of a wacky heat in a sense. You can actually plot it. That's me extracting the temperature from the simulation. What you see in red is the temperature of the vibration in plane as a function of time. And what you see in blue is the temperature of the vibration out of plane. So we start at 300 Kelvin. And you see that the in plane vibration immediately heats up and the out of plane vibration slowly, it's 20 picoseconds, not that slow, I know, but for laser is pretty slow, heat up much later. Okay, so it's actually a fairly simple symmetry argument for that. If you're thinking about an electron moving in a potential, I told you it was a gradient, right? So that's a little bit of assignment for today. So you're looking at the gradient of potential with respect to displacement. Okay? So imagine that you're moving in a potential which has a mirror symmetry. Okay, so that means that the potential is the same above the layer of graphene or below the layer of graphene. Okay. So now if I move the atom out of plane, okay, I'm looking at the gradient of this potential, okay? So if you look at the gradient, that's me drawing it, so it's not an exact gradient, please don't quote me on that. In the purple curve, that's just the derivative of the previous, mirror potential with respect to z, okay, the out of plane direction. So if you do the integral of that, you can immediately see that you started from even function, you took the derivative, so you have an odd function. If you do the integral of an odd function, you have 0, okay? So that tells you that, in principle, each time you have mirror symmetry in a material, in a two-dimensional material, you will only heat up vibration in plane, but not out of plane. So what it tells you is that when you think about heat in 2D material, you're really thinking about a different kind of beast, okay? You're thinking about things that behave differently if you shine a laser, as opposed to if you heat up the material, putting it in the oven, for example. It's physically different, okay? In one case, atoms move in 3 directions. In the other case, classically, okay, in the oven, atoms move in all directions. Under a laser, it moves in 2 directions. Okay, so there is anisotropic heat. I'm not sure I can patent this idea, but I still think it's a little bit crazy the way that we end up with those type of things. We can actually quantify that. We have done graphene, silicene, blue phosphorus. I don't know if some of you are familiar with those materials, but they are more and more asymmetric. So you have more and more broken symmetry, and you can see that it's actually, the difference between energy in plane and out of plane is actually get larger for graphene because it's perfectly planar. And when you have something that is all rigor, like blue phosphorine, is actually heat up classically in that case. So that's kind of, I'm sure a lot of you will continue in nanoscience a lot of you are gonna shine lasers onto 2-dimensional materials. So just think about that. Just think that when you heat up a 2D material in the future, you're actually heating the 2D material in plane if it has mirror symmetry, not the other. Okay, and that's actually just a sort of trend, a qualitative trend. Some of you may be familiar with tannin, germanine, blue phosphorus, silicene, hexagonal boron nitride, graphene. I mean, we make a lot of those materials at Northwestern. Actually, if some of you work with Professor Hersam, you may have made a new material during your summer internship. That would be a nice result, but it happens every day, as a matter of fact. And so this is actually how you think about that. The more asymmetric, the least mirror symmetric you have a material, the more heat that you're generating is messy in a sense. Is this anisotropic heat. So again, 90 kebrane phonons in one case and not in the other. This is not just me making claim here. This is actually it's been seen. So that's one of those crazy free electron lasers experiment. I really encourage you to Google that after this talk. It's exciting that we have those type of things. And And so basically, I mean, I will confuse the analysis here, but this is actually what they have seen. They have shined a laser on a tungsten disulfide layer, and what they have seen is exactly what they're seeing. So the material at short time expands in plane, and because it expands in plane, it contracts out of plane. So again, classically, if you put the material in the oven, it expands in all direction, as you would assume for most material. This material, when you shine light on it, it expands in plane, it contracts out of plane because just rapid thermal expansion. You can actually control that. We are in the process of doing that experimentally, but there are materials which have transitions between the mirror symmetric phase and the inversion symmetric phase. So there is, we have an active collaboration on that. I'm not gonna, sing, but basically what it tells you is a material, you can switch a transition and it will heat up differently. Okay, so the same mode that used to be cold, it will become warm and vice versa. So this is actually, as far as I know, is the first time someone has proposed electric control of heat. Okay, that's basically a thermal switch that you control with an electric field. So that's kind of the strange. It only works at 10 picoseconds. Okay, don't quote me on that. Some materials are better for that, but it's still something. This is one of those ideas where when you go at the scale of atoms, you can couple things like electric field or heat that look very different in principle. So that's one of many examples of such behavior. All right, so that might take a message. So basically what we have proven in my work was that semiconductors and nanomaterials, the time scale of heating are actually fairly slow, okay? And they are typically, larger than what is needed for the heat to get out of a device. So they actually matter. If you make, when some of you make devices, please think about heating as something very electronic heating or light heating as something which has no corresponding analogy with the rock, or at least maybe someone where you pour water on a rock as opposed to drop it in the water. For metals, they didn't go, but that actually does not hold. For metals, we recover something which is fairly well behaved with Twotemperature. We have this complex relaxation of electrons. We have actually a model for that, which is a generalized Twotemperature model, which is just one step further and we can use. If you have any question, if you are using some laser in your experiments, contact me. I can help you interpret those quantities that you are observing. And also what I want to say is as soon as you go into the nanoscale, you basically have those effects coming into play where you can structurally or electrically control heat. So even, old concepts like heat or thermodynamic concepts like chemical potential, all those things can be controlled at the nanoscale. So that's why hopefully I convince you that, there is a lot to look at. Even for simple concepts, you have to revisit them when you are considering a few atoms or 2D materials. All right, with that, I will conclude and I thank you for your attention.